So, yeah, as we mentioned before, our project kind of shifted from being, we had the intention to build a framework, now we more or less experimented and kind of explored the ideas we had in mind, and also had more of a focus on methylation data sets to see if we could actually use some of the ideas we had and make sense of these data. So just a couple of the tools we used, we have a few scripts on our repository, and the results that we more or less generated also included in the repository. So one of the tools we used a lot was the bed tools, because since we deal a lot with sequence and regions, genomic regions, bed tools was extremely useful to do things like intersections or difference between a set of sequences. We also used FIMO, which is a motif finding tool. So given a database of known motifs in a set of sequences, FIMO will scan these sequences and tell you which locations on these sequences where it thinks it has a pretty good match using that motif database. So we use JASPAR for the motif database in this case. We also use TomTom. So given a motif prediction or some kind of pattern we think we have in a sequence, it'll look this time in the database and tell us how well it can align this query to the motif it has in the database. To do de novo motif discovery, so FIMO actually scans for known motifs. We use this tool instead of MotifGP to do de novo discriminatory motif discovery. So in the case where you don't know what the motifs look like, you scan the sequences you have, and you try to come up with something you think is enriched in your data set. And we also use ChIP-seq for once we had some peaks to do annotations on what kind of genes are adjacent to this, or additional kinds of annotations about your peaks. So that's kind of like a broad schema of not necessarily all the experiments we did, but I guess like the major outline of what we did. So we started with some data sets, and for example, we had a differentially methylated region data set, so essentially range where we observe, or where some published data showed that they observed different kinds of methylation depending on if it was null mice or young mice. So these regions were extracted in the differentially methylated data set. And then from there, we could intersect or not with some other data set to get a subset of these regions. And then there's more or less like three things we wanted to do: peak enrichment, motif finding, and de novo motif discovery, which is the little boxes you see at the bottom. And to start, I'll quickly show we did some scanning of the motif finding to kind of see if there was something that would pop up a lot. And that's just a truncation of the table. The table had a bunch of matches, so as you can see, like thousands. So each of these numbers are accession numbers for a motif in the database. So you can see that some of them come up a lot. And we looked at first of all, the ones that were hypomethylated. And you can see that the same motif more or less come up. So that's kind of one of the questions we had. If we looked at one just independently and looked for motifs, would we see something drastically different? And it turns out, well, the most popular motif that found just by scanning is actually the same one in the hypo and hypermethylated data sets. Then we performed de novo motif discovery on these regions. So just to see if we could find something, we first looked at all the sequence of differentially methylated sequences and or regions, and see if we could find something. And we find a motif that actually aligns with a JASPAR motif, which is for arid 3D, and it has a modestly good p-value and e-value, which is a corrected p-value, which is still not terrible. But what's interesting is in this one, the second one at the bottom, we actually looked at the upmethylated or hypermethylated data set and did discriminative search against hypomethylated, and we actually find a motif that's much more well-defined, and it is much more degenerate and has actually a better alignment with the reference in JASPAR. So it was kind of interesting to actually make sense of that. I don't know, we had to look more and do more of the literature review to actually see if that makes sense or if it's just a false positive, but still interesting. And talk a bit about the instrument.
Yeah, sure. So we took all of these transcription factor binding site calls within these different regions, then annotated which transcription factors they were. This is just to count basically that table that Manuel just showed, but with unreadable transcription factor names. But this giant bar over here is actually REB1, and what's interesting, so this is the hypomethylated genes, these are the hypomethylated genes, And it came up in both of them, kind of suggesting that it's probably just matching, indiscriminately across the kind of regions. And in fact, when you looked at the kind of sequences, it was basically just like CA, kind of like dimeric repeats and things that were matching to this motif. So it's probably something to try and screen out in FEMO for people that are trying to do this in the future. So what we did is to subtract, find the lead transcription factors that were specific and either hypo or hypomethylated, and then go and annotate genes to those. And in fact, in the hypomethylated, so the regions that are more methylated in old mice, so they're probably preventing transcription factor binding in those regions. One of the genes that came up was CDK6. In fact, this accompanying RNA-seq, and it looks like it's 1.5-fold higher expressed in younger mice, so it's actually kind of being downregulated in this expression. And when I don't have a slide for this, but I also checked the transcription factor expressions, and all of those transcription factors are pretty level, so it's kind of seems pretty convincing that there's actually a regulation happening through the DNA methylation of this expression. And CDK6 is kind of known to be involved in hematopoietic stem cell quiescence. So in fact, the specific cells being looked at here were the stem cells that produce blood in older mice, and they're known to be